this might be a little bit intimidating at first, but we're going to be drawing the product of all of these reactions. Now, unfortunately, there's no getting around learning these reactions. You're going to be expected to know all of them. You just have to get into your head what each of these reactions does to an alkene, what bonds are formed and what bonds are broken, and you also have to know what we call the regiochemistry, so that is Markovnikov or anti-Markovnikov, and the stereochemistry of each reaction. Now, if you're having a hard time keeping it all straight, I might refer you to the 3-bucket technique. I have a summary sheet on that and also cover it in the webinar for this topic. There are 3 main patterns these reactions tend to fall into, but this is really just the basics. Knowing these reactions is really just like learning the moves in chess. Ultimately, that's just the first step before you be asked to play. The questions you'll get on an exam are usually not going to be this straightforward. Okay, so with that encouraging introduction, let's get started. So let's look at this first reaction, MCPBA. When you see this, you know that you just have to know that this is an epoxidation reaction. Okay, MCPBA is what's called peroxy acid. You might also sometimes see RCO3H in here as well. Now this makes an epoxide. So let's actually draw the reaction product here. Okay, so here I've drawn the 2 products of this reaction. Now, you might ask, why have I drawn 2 products of this reaction? Well, the fact is, actually, these are not exactly the same. If you studied stereochemistry chapter of your course, you might know that recognize these 2 compounds are enantiomers. And in fact, we'll deal with questions involving relationships in a subsequent section. But it's enough for here just to know that we're going to break a carbon-carbon pi bond, and we're going to form 2 new carbon-oxygen bonds using the MCPBA. And this is what we call an epoxide. And it would be acceptable to draw it either with those bonds coming out as a wedge or both those bonds coming out as a dash. And also, pay attention to the bonds that are forming and breaking this reaction. We're, of course, forming 2 new carbon-oxygen bonds. We're breaking a carbon-carbon pi bond. The regiochemistry of this reaction is actually not applicable because oxygen, the same atom, is adding to both carbons of the alkene, so there's not really a regiochemistry issue here. However, stereochemistry is very important. It's very important to show that the oxygen, both bonds, new bonds to oxygen, are on the same face of the alkene, so either both wedges or both dashes, and this is what we refer to as syn stereochemistry. Now let's look at the next reaction of this alkene with HCl, so hydrochloric acid. This is going to break the carbon-carbon pi bond, as before, and we're going to form a new bond between carbon and hydrogen, and a bond between carbon and chlorine. Now, you can't actually see the bond between carbon and hydrogen here because we've not drawn it. It's like implicit in a carbon line drawing, but it's there. Wasn't there before. And we also have a new carbon-chlorine bond. Now, the regiochemistry of this reaction, we call it regiochemistry, is very important. Hydrogen and chlorine are different atoms, and it's important to show that chlorine adds to the most substituted end of the alkene, and hydrogen adds to the least substituted end of that alkene. We say most substituted because this carbon is added, this is attached to 2 carbons, it's only attached to 1 carbon and a hydrogen here. Okay, that's what we refer to as Markovnikov selectivity or regioselectivity. Now, the stereochemistry of this reaction is interesting in that chlorine and the hydrogen, although it's not shown, can add either to the same side of the alkene or to opposite sides of the alkene. Now, same side, that's called syn, and the opposite side is called anti. It's actually a mixture of syn and anti, although you can't really tell the difference here because it doesn't really produce different products. Whether the hydrogen adds to the front or the back, or they're on the same side or the opposite side, it's still the same compound. So here, the consequences of that mixture of stereochemistry is not consequential. All right, let's look at this reaction with OSO4 and NaHSO3. Now, OSO4 we call osmium tetroxide, and NaHSO3 is what we call sodium bisulfite. It's sometimes seen along with osmium. It's not absolutely crucial. Sometimes it's used to get the osmium off the oxygens in the end. So let's have a look at the product we get here. Okay, here notice that we're breaking the carbon-carbon pi bond, and we're forming a carbon-to-oxygen bond on both carbons. This reaction is called dihydroxylation because we are forming 2 hydroxyl groups, okay? And this product is called a diol, or usually called a vicinal diol to say that those alcohols are on adjacent carbons. And notice here that I draw 2 products, again, just like we did with the epoxidation example. They might look the same, but they're actually enantiomers of each other. They're non-superimposable mirror images of each other. But since the question itself asks for us to just draw 1 product, either one of these would be acceptable. Now, just like with epoxidation, we're adding the same group, in this case OH, to both sides of the alkene, or both carbons of the alkene. So it's neither Markovnikov nor anti-Markovnikov. So for that reason, put not applicable here for regiochemistry. However, the stereochemistry is very important. Notice that the 2 OH groups both have wedges, or dashes in this case, which is to say that they both added to the same face of the alkene. So that is to say that stereochemistry here is syn. Now in this next reaction, we're taking this alkene and treating it with bromine, Br2, and although not always, occasionally you will also see a solvent listed, and CCl4 is carbon tetrachloride. It's a solvent that bromine is dissolved in, and actually it's not going to react with the alkene at all, but you'll see later this is to differentiate itself from other solvents which possibly could react with the bromonium ion we form in the middle. So let's show the product of this reaction. All right, notice that we are breaking the carbon-carbon pi bond, and we're forming 2 new carbon-bromine bonds. Now, because we're adding the identical groups to either side or either carbon of the alkene, there's no question of regiochemistry in this case. We can't have Markovnikov or anti-Markovnikov products. However, there is an exception to this we'll talk about when we go through bromine and water. As far as the stereochemistry is concerned, however, notice that the one bromine is a wedge here, one is a dash, and here to the right I've shown the other product one could draw as the product of this reaction, where this bromine is a dash and this bromine is a wedge. And since they've added to opposite faces of the alkene, we call this anti-addition. Okay, so the stereochemistry of the addition between bromine and the alkene is anti. All right, next we'll take this alkene and treat it with H3O+. Now there's a few different ways to write this reaction actually. H3O+ is one common way, but you might also see water in the presence of H2SO4, so sulfuric acid. Okay, and essentially this is going to add hydrogen and OH, or essentially add water across a double bond. So let's show the product of this reaction. Okay, so here the product is, notice we formed a bond between carbon and oxygen here, and we've also formed a bond, although it's hard to see. We have 1 carbon-hydrogen bond here, but now after this reaction we have 2 carbon-hydrogen bonds. We just haven't drawn them all in. Okay, so we're adding carbon to OH and forming carbon to H. And the regiochemistry of this reaction is, again, in the category of this reaction with HCl, we'll call Markovnikov. So that is that the OH group is adding to the more substituted end of the carbon. Notice this carbon is attached to 2 carbon atoms. And this less substituted end of the alkene is attached to 1 carbon and 1 hydrogen. This gains another hydrogen. So this is what we call the less substituted end. So again, it has Markovnikov regioselectivity. Just like with the chlorine HCl reaction, there's no stereochemistry selection in this reaction, no stereoselectivity. That is that the OH and the new H can either add to the same side of the alkene or on opposite sides. So in fact, we had a mixture. Although here we can't, again, tell the difference between the syn product and the anti-product because they both give us the identical product in this case. Okay, so this is the product of the reaction of acidic water with an alkene. All right, our next example is actually quite an interesting one. So we're going to start with this alkene and treat it with BH3, so that's borane. And the second step, we're going to treat with NaOH and H2O2, so sodium hydroxide and hydrogen peroxide. And as we'll see, the product we're going to get, I'll just draw it here, is that we're breaking the carbon-carbon pi bond, and we're forming a new bond between carbon and OH, and we're also forming a carbon-hydrogen bond. Now, what's interesting about this reaction is that in previous examples, we saw how hydrogen was adding to the less substituted end of our alkene. So for example, with HCl, it added here, and with H3O+, it added here. Now in this case, we're actually taking the more substituted end of the alkene, and that's where our new carbon-hydrogen bond is forming. And we're forming a carbon-oxygen bond on the less substituted end of the alkene. So for that reason, the fact that hydrogen is on the more substituted and OH is on the less substituted, we refer to this as anti-Markovnikov regiochemistry or regioselectivity. Okay. And the second thing to note with this reaction is that the hydrogen and the OH are arriving on the same side of the alkene, so they are syn. Notice these are both wedges. Now, again, we could also draw a product. This would also be an acceptable answer to this question, where hydrogen is a dash and the OH is a dash. And again, just like in the MCPBA example and the OSO4 example, these two would be enantiomers of each other, and either one of them is acceptable. But the stereochemistry of this reaction is syn. So this is called hydroboration. This reaction here with palladium on carbon and D2 is a little bit of a curveball. So we're starting with an alkene, adding palladium on carbon. Usually we have H2, and this reaction is called hydrogenation. But the products of this reaction will be a little bit boring if we just add H2, so I've decided to throw in D2 instead. And this is actually a very common type of exam question. Deuterium is the heavy isotope of hydrogen, so it behaves just like hydrogen in every respect, almost every respect. It acts like a label. We can actually detect the difference between hydrogen and deuterium if we're curious about this. So when we treat this alkene with palladium on carbon and deuterium, let's draw the products here. We're breaking a carbon-carbon pi bond, and we're forming 2 new bonds on each of these carbons, so one to deuterium and the other one to deuterium. So both ends of that, what used to be our alkene, form a new bond to deuterium. The regiochemistry doesn't apply here because we're adding the same group to each side of the alkene, so just like with oxidation, dihydroxylation, bromination doesn't matter. Now, what is important to note is that the fact that these deuteriums are adding to the same side of the alkene, so either both syn as wedges or both syn as dashes here. And actually, believe it or not, these two compounds are enantiomers of each other. This is not a stereocenter here on the left because it's attached to 2 identical methyl groups, but on the right-hand side, this has got a CH3, deuterium, there's a hydrogen, dashed hydrogen in the back, and then there's this carbon group. So that actually is a stereocenter. There's 4 different groups attached to that carbon. So these are enantiomers of each other, and either one of these would be acceptable as an answer. So if we had just used hydrogen, H2, this would not be a stereocenter. This carbon would be attached to 2 hydrogens. So this actually, we just form one product. But I decided to throw in the deuterium here because that shows us an example where we can form enantiomers, and you might see this tested. So it's important to be aware of this type of example. And our last example here is a really interesting case. So starting with an alkene, we're going to add bromine, just like we did in this previous example. However, it's going to be in the presence of water. And as we'll see, this is going to throw the products it gives a slightly different product of this reaction than just with bromination. So when we show the products of this reaction, notice how we're forming a new we're breaking carbon-carbon pi. First of all, as we do with every single one of these reactions, we're always breaking carbon-carbon pi. These are addition reactions. We're forming a new carbon to OH bond on the more substituted end of the alkene, and we're forming a carbon-bromine bond on the less substituted end. And we also have the enantiomer shown here. So this is another product of the reaction that would be an acceptable answer to this question. Now, the regiochemistry is very interesting here. It's very important to show that the OH is added to the more substituted end and not to the less substituted end. And this stems from the mechanism of this reaction itself, which I won't be going through in this slide, but it is covered, where we have a bromonium ion and water attacking the more substituted end of the bromonium ion from the back, from behind, and this opens up a 3-membered ring. And it's very important that you show this as the major product. So this is technically, I guess, what we refer to as Markovnikov regioselectivity, just like with HCl and H3O+, and then the water is added to the more substituted end. Now, the stereochemistry is also very important. Just like in this previous example with bromine, we have anti-stereochemistry, which gives us the trans product. And so the OH is wedge and bromine is a dash, and so it's important to show that stereochemistry. So in conclusion, just recall that every single reaction we talked about here, we're breaking a carbon-carbon pi bond, every single one. And pay very close attention to the regiochemistry of each reaction, so Markovnikov, anti-Markovnikov, or not applicable, and the stereochemistry. Is it syn, is it anti, or is it a mixture of both? And of course, it's very important to know what each of these reagents does and the mechanism for these reagents and reactions where applicable, because this is really going to be the bare minimum amount of knowledge to go into your exam with if you hope to be able to succeed. You can take it for granted that your instructor will assume that you know all this stuff, and they're probably going to be testing you on a little bit more twisted examples of these questions, which I've shown you right here. So we'll talk about those in future videos, but